Hope everyone is doing well. And so in last class, we talked about how eigenvalues of graphs can give us information about connectivity. And towards the end, we discussed that it not only gives information about whether the graph is connected, but it can also tell you some kind of measure about how connected the graph is. So usually we think of connectivity as just kind of a discrete quantity. Either the graph is connected or not. But now you want to say some graphs are better connected than the others. Okay. So today we'll explore this connection further and see how, if you have a high spectral gap, then it is possible to get an algorithm easily. And then we'll use this as our lever to get a small space algorithm for connectivity. Okay. And a couple of announcements. Today, I'll have office hours from 1:30 to 2:30, and that will be on Zoom. And you can find the link on our class website, or I probably won't remember right now. And also for everyone waiting on the wait list, I've assigned PTs for them. If you still haven't gotten a PT after that, let me know, and there might still be space. Okay. All right. So towards the end of last lecture, we kind of studied this statement that if your second largest eigenvalue lambda is far from 1, then the graph is very well connected in that any two vertices have small distance between them. Okay. Since we will be using this terminology a lot, let's give it a name. And it's also something that shows up in many places. Okay, so let me just say a definition. Delta of G equals infinity if G is disconnected and is equal to okay. So delta of G is the diameter of graph G. Okay, so if the graph is disconnected, then it is defined to be infinity. But if the graph is connected, then it measures, among all the vertices that you have, which two are furthest apart. Okay, like here and here, maybe these two are the vertices where the shortest path between them is longest. Okay, it's the length of the longest, shortest path between any two vertices. Okay. So, if you do a couple of examples, so let's say we take the path graph. Is 1, 2, up to n. Now, what is the delta of path graph? How far are two vertices in here? So if I take these two vertices, the distance between them is 1. If I take this and this, the distance is 2. If I take this and this, the distance is 3, and so on. But what is the length of the longest, shortest path? As before, if you want to, you can either chat or just answer, by unmuting yourself. So what is the diameter of the path graph? Well, the furthest two vertices are 1 and n. So the diameter is n minus 1. Okay. And let's take another example. So let's say my graph now is something like this. It's like a tree. I have maybe, this is the, okay. Let's say my graph is the star graph. Okay. So there's a center node and it is connected to everything else. So this is 1, 2, 3, all the way up to n minus 1. Okay, so what's the diameter of the star graph? Well, if I take any two vertices here, they're kind of at the same distance, so it's just 2. Okay. And finally, let's do one more example. And this is let's say maybe I put some number of vertices here, and there are 4 vertices like this. I'm just taking a random example, so this will show up in a bit again. Okay. So what is the diameter here? Kind of looks like a tree where here you have a very high branching factor, and then these twigs are kind of 5 vertices each, right? So if I want the diameter here, if I take this leaf and this leaf, the way to connect them is to go all the way up to the root and then come back, right? So 1, 2, 3, 4, 5, 6, 7, 8. So this is 8. Okay. So different graphs might have different diameters, and in some sense, diameter being small indicates that the graph is well connected. Okay. And a spectral graph theorem, in other words, can be restated as essentially saying, in this notation, delta of G is at most this much. Right? Okay, any questions? Okay. So why is this extra connectivity in the form of diameter helpful? So why do we expect it to be somewhat useful for us? Okay, let's talk about that. Okay, and so maybe one way to think about this is to look at examples again. So let me call this what's a good name? Spider graph. Okay, so let's take the 2 examples. First example is the path graph. And the second example is the spider graph. Okay, so let's go back to the original question that we are trying to solve, right? So what was the problem that we're trying to solve? The problem that we're trying to solve is undirected ST connectivity, right? So we're given 2 vertices S comma T, and we want to know, like, if they're connected, and if so, how much time do they take? Okay, of course, these 2 graphs are connected, but let's see how, is there an algorithm which will do better, at least on these graphs? Or can it separate between these 2 graphs? And then we'll gain some intuition from that. Okay. So let's take something like breadth first search. So how much space do they need on these graphs? So the spider graph somehow seems better well connected, but breadth first search and depth first search both take a lot of space on these graphs. Okay. In particular, on the path graph, both take n bits. On the path graph, they take n bits. And on the spider graph also, they take roughly n bits. Okay. So even though the spider graph seems easier in that the diameter is very small, your algorithms, breadth first search and depth first search, can still take a long time. Okay, do you agree with this? Any questions about that? My claim is that even though the spider graph seems simpler for connectivity in that the shortest paths are all small, the basic algorithms that we use for connectivity do not exploit that. They still take n bits of memory. Because imagine you do breadth first search starting from here, right? You keep going like this, and eventually you'll reach here. And until then, you have to keep track of all of the flags. And there's no easy way to short circuit that. Okay? Any questions about that? Okay. But my claim is that there is a different algorithm which can actually do better, at least in terms of space, if I tell you that the shortest paths are all small. Okay, so what do I mean? So imagine I give you a graph and I tell you either okay, so this is the same undirected ST connectivity problem, but now imagine I also give you a promise. Okay, the promise is that this graph G is somehow well structured. Okay, so the promise is that I'm not giving you the absolutely hardest possible instance of this problem. The promise is that either G is disconnected or actually, let me just say it this way. Okay, so there is some parameter T such that every connected piece of G has diameter at most T. You know, even think T is like 8 for now. Okay, so in some sense, I'm telling you the graph is basically part of pieces. like this. These are all the connected components. Of G have diameter less than or equal to. Okay. So any two vertices in the same connected component have a shortest path of length at most t. So if S is somewhere here, then either S and T are disconnected, or there is a path of length at most t between S and T. Okay. So in other words, the promise tells you that either S comma T are disconnected, or okay, again, think of T as being 8. So we are making the problem easier by assuming something seemingly very strong about the graph, but this will be a starting point for the full algorithm. Okay, we are trying to identify easy cases of the problem, and then we'll see how we can reduce all cases to these easy cases. Okay. All right. So if I tell you this promise holds, is there a better algorithm? As we just remarked, breadth first search and depth first search are not good even in this case. Even if I have this promise, like a single spider graph, they still take a lot of space. But is there a different algorithm, a different way to optimize for space when you have this? Any suggestions?
So we can enumerate all paths of length at most t, g.
Exactly, right? So the point is that we're not worried so much about time, and space has this amazing thing that unlike time, you can reuse it a lot. Okay, so I'll call that, in some sense, it's like a naive brute force algorithm. Okay, so what is a brute force algorithm going to be? So explore all paths of length less than or equal to t from S. If you reach in these explorations, we output yes. Okay. If not, say no. Okay, makes sense. And so, like, for example, for the spider graph, what you would say is I'm starting here. I'm going to explore all paths of length 1, all paths of length 2, all paths of length 3, all paths of length 4. When I do all paths of length 5, I would just do this. Okay, and then come back. All paths of length 6, and so on. All right. And what is so nice about this algorithm? I mean, it's a brute force algorithm. You're not even looking at the graph. You're kind of exploring all possible paths of length t, right? So it's like saying, if I ask you to go from place 1 to place 2, I'll take all roads of length 1, I'll come back to the origin, I'll take all roads of length 2, come back to or start, take all paths of length 3, and so on, right? The win here is in terms of space. So how much space do we need to explore all paths of length at most 10? All right. So how do you describe this? You will say somehow take first neighbor. Okay. What do I mean by first neighbor? So our graph G, let's say you have the adjacency list representation. Okay. So the way the graph is represented, let's say we are assuming it's the adjacency list representation for now, meaning for each vertex, you have a list of its neighbors. Okay. I can say, starting from S, take the first neighbor of S. This is vertex S. Take the first neighbor of S. Okay. And then maybe you'll say, take 10th neighbor of wherever you are. And you take the 5th neighbor of wherever you are, and so on, up to T steps. Okay. So in some sense, I'm exploring the graph locally. I look at where I am. I have some neighbors. I say, go to the 10th neighbor. I jump, and then I'll say, go to the 5th neighbor, jump, and then so on. Okay. If in T steps, I don't see my target vertex, then I start from scratch again. Okay. Does the algorithm make sense? Any questions about the algorithm? It's kind of a little bit oblivious to what the graph is doing, right? So the space complexity is just determined by the sequence of which neighbor you're taking in terms of the position in the list. Okay, I'll say take the first one, take the 5th one, take the 17th one, maybe take the 37th one, and so on. Okay. There's a question saying, how do you ensure you don't repeatedly visit the same vertex? Actually, we might repeatedly visit the same vertex. That's okay, as long as we are not going to run in an infinite loop. Okay. And I'll talk about that in a second, right? So it's okay to visit the same vertex multiple times. In fact, we will visit the same vertex. So the time complexity will be pretty bad. But right now, we're only optimizing for space. As I said, ideally, we would like to have the best of both worlds. But since the space complexity was very bad to begin with, let's see if we can ignore time and get something better for space. And as we'll see, it'll work out well in both directions. Okay. So what we're saying is starting from S, you have the neighbors listed in some order, right? Maybe this is the first neighbor, second neighbor, and this is the 10th neighbor, right? And then this vertex also has some numbering on its neighbors. This vertex has some numbering on its neighbors. This vertex has some numbering on its neighbors. Okay. And just to be maybe simpler, let's assume the graph is deregular. There is a version of the algorithm in general, but let's just assume the graph is deregular. Okay. So the space complexity is going to be the following. To represent this exploration path, what do I need? Right? I need a number from 1 through D. I need another number from 1 through D, and so on. Okay. So we are going to store something which doesn't even depend on the graph in some sense. It only depends on the degree. We're going to store a sequence of t numbers, each from the range 1 through d. And I store the sequence and then I explore it. If this says fifth, I take the fifth neighbor. If this says 17, I take the 17th neighbor. If this says 31, I take the 31st neighbor. It might go back, it might repeat the same vertex, but we're just going to ensure that the entire sequence is not repeated again. Okay, vertices might be repeated multiple times, but the whole sequence is not going to be repeated. Okay, does that make sense, Nikolai? Okay, so we are keeping track of just the relative numbering of the sequence of vertices we are visiting. Okay, which neighbor are you visiting? Which neighbor are you visiting? Okay, not the identity of the vertex, but just the name of the neighbor relative to myself. Okay, I have 1 through d neighbors. What is my 17th neighbor? That might be a different vertex completely, but that's okay. Okay, and this algorithm is not using any randomness, right? We're just exploring or enumerating all possible sequences of this form. Okay, so you start from S, essentially you enumerate all possible lengths of length at most t. And if any one of them hits our target vertex, we are very happy. Okay. So one request, I see some questions, very good questions popping up, but if you can chat it to everybody, I think that will make sense. That's more like a class where you ask questions, others also listen, and it helps everybody. Okay. All right. So in terms of space complexity, what do we need to store? We need to store this entire sequence. So we need to store t numbers, each from range 1 all the way up to d. Okay, so this is log d base 2 times t. Okay, and we need to store where we are. In this exploration, every time you store where you are, you don't have to remember the entire path, but you need to remember exactly where you are so that you can pick, okay, if I say 17th neighbor, you know whose 17th neighbor you are looking at. Okay. So this is for the enumeration path. And then we need to store which vertex we are at. And this is log n base 2. Okay, we have to store the name of the vertex, and there are n vertices, so you have to store this much memory. And then we always keep track of the target t. Because you want to compare, am I at the target already? Am I at the target already? And so on. Okay. You always show the target and store the source. Because once you finish this thing and you don't reach the target, you have to reset and start again. Okay. So the total memory is basically order of log n plus the degree times t. Okay, and we are fine with log n usually, so we have to only worry about, predominantly about this. Okay. So there's a question, if we don't want to repeat the same sequence, do we not need to store every sequence that we traverse and not just one sequence? Exactly. So the same question, it's both are related questions. So the way to do this is the following, right? So just imagine if I ask you to write a Python program for generating all possible sequences of length d, what would you do? So question. Okay, so any suggestions? If I ask you to write a program, what would you do? So let's say I just ask you to print stuff, keep printing out all possible sequences. Excellent suggestion. So Derek here has a suggestion, like a base D number to get every possible sequence, or you can, basically say something like this. I start with everything being 1, 1, 1. Okay, and then I change the last one through 1 through D. Right? And then I change the one before to be 2 and enumerate this, all possibilities, and so on. Okay? So in some sense, there is like an ordering you can impose, and that is enough. Does it make sense? So, you can essentially think of it as I store these values, and for every fixing, I try every possible stuff of, one coordinate at a time. Okay. All right. And eventually you will end up doing everything. Another way to think about this is that you're basically having T for loops. Right? So, maybe it's not exactly this much, but let's say this is O of this. So we will have okay. So you have T for loops. So to keep track of this, you just need to store these values. Okay. So that's only T counters. Or as Derek suggested here, you can also use some base D number, but then you have to figure out how to get the individual things out, but that can be done as well. Okay. Any other questions? All right. So, it's not immediate, but this can be done using some kind of standard programming things like, having multiple for loops. Okay. So what's the summary of all of this? So we learned something interesting, two things which are very interesting. Cool. Okay. So undirected connectivity is solvable with space log n plus log d times t, where t is the diameter of the connected pieces. Okay. So there is at least one potentially easy case for solving undirected ST connectivity. But of course, this, it doesn't solve us, immediately help us with the main problem, because if I take a graph like the path graph, the diameter is n minus 1. So you're ending up with even worse space, n minus 1, right? But on the other hand, at least for the case of the spider graph, this might help, right? So spider graph, the diameter was just 8. So we made some progress. Okay. All right. So we have to deal with both of these cases. One is this, so the degree itself could be big. And then we also have to deal with the case that the diameter also can be big. All right. So we have to deal with both of these. Okay. So one annoying thing with the diameter is that it's kind of a combinatorial quantity, which is somewhat brittle. Okay. So instead of diameter, we will use another surrogate, which is the spectral gap. And that is coming from, this is where our spectral graph theory comes to the rescue. Okay. So small diameter graphs are nice for connectivity, but the problem is that diameter is kind of a brittle concept. Okay. So it's kind of a concept which is very combinatorial and not very easy to handle. So let me kind of consider another easy case. Okay, so this is what we just saw. So Arush has an excellent question. What exactly does brittle mean here? It's a qualitative term. I just mean that it's a combinatorial quantity which is hard to keep track of when I change the graph. Okay. So if I delete an edge, somehow the diameter can change a lot. Okay. So that's the sense in which we might want to be a little bit careful with diameter, but right now it's just like a conceptual thing. We want things which are more amenable to analytic methods. Okay, analytic meaning things which can be changed smoothly. In some sense, diameter can also be changed smoothly, but it's harder to track. Okay. All right. So this other quantity is basically what the spectrum, this is where the spectrum really helps. So let me change this to the form. So this was our first easy case. And the second easy case, or second case that we know how to solve, is going to be the following. Okay, so I'm replacing the condition on the diameter of the connected parts. Instead of requiring that, okay, you have a graph G, I'm trying to solve ST connectivity on it. We are going to require that the connected pieces themselves have high spectral gap, meaning the second largest eigenvalue of every connected piece is at most 9/10. Okay. There's a comment here. I thought maybe it isn't useful as a bound because it's susceptible to combinatoric explosion. It's not explosion, but basically we want to reduce the general case to cases where the graphs have small diameter. So that's exactly what we're going to do. We're going to reduce the general case to graphs which have small diameter, and then use this brute force algorithm on this new graph, right? But instead of tracking the diameter, which becomes harder to track when you make these operations, we are going to track the spectral gap, because this is where linear algebra gives us a huge advantage. Okay? I mean, this is magical, right? In some sense, you're pulling a rabbit out of the hat by saying, I'm going to focus on the spectral gap. Why? Or why was that good intuition? That's in some sense why this problem took so long to solve. Okay. Does it make sense, Jay? Okay. So what is this guarantee saying? This is saying that, maybe my graph has these pieces, right? Different pieces. My S vertex is somewhere here. This is S. It could be disconnected, but every connected piece okay, every piece has second largest eigenvalue at most 9/10. Why does this help us? Well, it helps us immediately because SGT3, our theorem number 3, tells us that lambda is less than or equal to 9/10, implies the diameter of the connected pieces okay? So spectral graph theorem number 3 tells us that if you have small diameter, if you have spectral gap, then you have small diameter. In particular, if your second largest is at most 9/10, then the diameter is at most log n, choose 10/9. So it's just O of log n. Okay? So putting these two things together with the brute force algorithm, we get space complexity, which is O of log n plus log d times log n. Okay. So does this make sense? So if our graph has, maybe let me write it properly. Okay, so if our graph has high spectral gap, something like 9/10, then I can solve it in almost log space. There's this additional log factor in front of the degree, but I'm almost done. Okay, does this make sense? Any questions about this picture? Okay, so what does this mean? I mean, this is a very strong condition, right? I'm saying, okay, assume the degree is a constant, assume every connected piece has spectral gap at most 9/10, two very strong or seemingly strong assumptions. But if you have these assumptions, then the brute force algorithm. Okay, so do you agree with this? So the summary of everything we've discussed so far should be this. If the graph has constant degree and all the connected pieces have high spectral gap, meaning the second largest eigenvalue is bounded away from 1 by constant amount, like 9/10. This constant is not important. It could be 9/10, half, it doesn't quite matter. Then you are good. You have a log n space algorithm. Okay. Of course, we have, these two are strong assumptions. We have to somehow figure out how to get there, but we'll do that. Okay. Any questions about this? Okay. So, and I should say that, okay. So in some sense, people knew that you can use the spectral gap as a surrogate for diameter being small, but no one thought of like, okay, maybe this should be something that could be useful for solving the ST connectivity problem. Okay, because it seems like a very strong assumption, right? And so Reingold's main idea, which is what we're going to explore, is the following. So we are given as input an original graph G, some starting vertex S, a target vertex T, and we want to know if these are connected in the graph G. Okay. He said, given this, I'm going to find a different instance, G bar, S bar, and T bar, such that the vertices S comma T are connected in G if and only if the vertices S bar comma T bar are connected in G bar. Okay. And you have two new properties. The spectral gap of G bar is so the second largest eigenvalue of G bar is better than this second largest eigenvalue of G. Okay. The smaller the second largest eigenvalue is, the better connected the graph is, and the easier the instance is for us. Okay. Saying, let's find a different instance where I make some progress. So the number of vertices might have changed. It's a completely different graph, but at least the spectral gap would have improved. Okay. And here, I mean of the connected pieces. Okay. And the degree is not much worse. Okay. So we're going to gradually transform our input to a different input where the spectral gap is better and the degree is not much worse. So somehow you have to make sure that the trade-off goes in your direction, right? So you have this sort of 1 over lambda there, right? So in the denominator, so you have to make sure that the trade-off goes in your direction. Okay. So that's the overall template. We want to find some operations which will modify the graph so that we kind of move towards this easy case. The case where the degree is small and every connected piece has high spectral gap. Okay. And that's what we're going to talk about. So in some sense, we're going to talk about this ST connectivity problem a little bit more, but then abstract away and mainly talk about this operation for improving the spectral gap, which has found its own sort of set of applications, and it's an amazingly useful concept. Okay, so let's take a 5-minute break, and when we come back, we'll kind of take this big picture of transforming graphs into some things which are easier and see how to do that. All right, so let's resume in 5 minutes. Okay, so before going on, I want to first describe that you can get a very good starting point, at least in terms of the degree, by using a sort of a simple trick. Okay, so what is this trick? Again, I'm only going to define the high-level sketch. To actually show how to implement it in small space, you have to write down the pseudocode and make sure the details work out. But those are not as interesting as the main idea, so I'm going to skip that. Okay. So suppose we are given a graph G and S comma T, the source and target. I'm going to give a new graph G bar, S bar, and T bar, like a new source vertex and new target vertex, such that S comma T are connected in G if and only if S bar comma T bar are connected in G bar. Okay, that's number one. And two is that G bar is a 4 regular graph. Okay, so every vertex in G bar only has 4 other neighbors. Okay. And thirdly, this is what I'm going to skip under the rug. It just requires a little bit of care in terms of how you code it up, but basically make sure that you can get Oracle access to right? So what does this mean? Somehow you should be able to produce G bar in small space. Like if I ask, okay, here's vertex number 11, tell me what is the 17th neighbor of vertex number 11 in G bar, you should be able to do that in small space, right? Because remember, space is our main resource. If you end up using too much space to make this conversion, then you lost the battle already, right? But this is, you just need to make sure you're using the right like data structure and representation. So, but it's not as important for the main ideas, okay? But how do we do this? It kind of seems amazing that you can reduce the degree all the way to number 4, okay? And the reason we can do that is the following. So I'll give it by an example, and then I'll describe how it is done, like the formal process. So let's say this is my graph. Okay. So if this is my graph, what I'm going to do is replace, kind of add new vertices on every edge. Okay. I'm going to increase the number of vertices, but that's okay because the degree is going to be small and the number of vertices is only going to be not so large that log of that is going to make a difference. Okay. So the way I'm going to do it is essentially create 2 new vertices along each edge. Okay. You know what? Maybe let me do it in a slightly different. So okay. So intuitively, you take every edge, kind of break it up at the endpoints, wherever they are, create new vertices, and connect those things. Okay. So I'm going to go from here to this new graph where I create things like this. I delete the old edges and connect these things. It's like a nice coloring project. Okay. And that's basically it. Okay. So, and then, so add a local cycle. Okay. So okay, so for each edge, something like here, I create 2 vertices, like this purple vertex and this blue vertex. Okay, one at near the 2 endpoints. Okay. After that, you add a local cycle at each old vertex. Okay. So when I do this, for each point here, each old vertex, I would create certain number of new vertices which corresponds to the old degree. If I have 10 edges, I have now created 10 new vertices. Okay. So locally, it looks like something like this, right? So this is my old vertex. And let's say I have edges like this. Now I'm breaking this up by creating new vertices. Okay. And then I create a cycle among these things. Okay. You can keep the old vertex or not. Let's say we don't keep the old vertex. It doesn't matter. Okay. So for all of these things, you create a cycle like this. Okay. And you connect the cycles with these edges. All right. And finally, add self loops to the graph. Okay, and finally, we'll add some self loops so that, things are nice linear algebraically. So like this. Okay. So the number of edges is, because I'm creating a cycle, I will get degree 2. And every vertex will have one extra edge to another cycle. And then you have the self loop. So total degree is 4. Okay. So any questions about this kind of construction? I know my pictorial skills are somewhat limited, but hopefully you get a sense by the zoom in that we did. Okay. And then, oops, you also have the self loops. Right. So you keep the old edges. So like, the cycles are themselves connected by these edges. Okay. Any questions about this transformation? It's like you're snipping off the edges and then connecting them through the cycles. There's a question, how did you get total degree 4? Right? So why is it total degree 4? Well, so when I create this cycle, I'm going to get degree 2. Okay. And every vertex here has one sort of edge to another cycle, right? Because it was part of this original edge, the old edge. You're keeping this middle segment. You're snipping the end points, kind of breaking the ends of the edge, right? And then you're keeping the middle segment as it is. So this is degree 2. This is kind of giving the third edge. And then the self loop gives you one more edge. So the degree is 4. Okay, I mean, as long as it's a constant, we are fine, but precisely it's 4 here. All right. The number of vertices has increased. The number of vertices now is basically the number of edges in the original graph, but that's okay. We don't have to worry about that. Okay. And there are some sort of annoying corner cases, like there is, what if you do, yeah, there's we do not consider the old vertex. This vertex is basically cut off, is thrown out. Okay, that's not part of the graph anymore. Okay, and S bar, you can just take anything in this cycle corresponding to S, and T bar can be anything corresponding to the cycle in T. All right. And there's some corner cases, like, what if I have an isolated vertex? There you're essentially saying I'm going to create 4 cycles, 4 self loops, sorry. Right? So there's some corner cases to deal with, but the main thing is you're breaking up these edges to be at the endpoints. Okay, does that make sense? So it's not 5 because we are basically chopping this off. Again, that's a convention. Even if it's 5, it would have been fine, but we're just throwing that away because this has high degree, right? So we don't want to have high degree vertices. So maybe to do an example, like let's say I had these spider, maybe something like this. Okay, so now I would get new vertices here. Okay, and same things before, like here. And so on and so forth. You had to get new cycles here, like, okay, does that make sense? Yeah, there are various ways to do this, but this is the simplest. Is there any requirement about the ordering of the vertices inside the cycle? You can impose an ordering because we have an ordering in terms of the adjacency list, right? So it's not technically needed. There's no importance to the ordering, but it is important to be consistent with the ordering. Okay, so basically, this is, you have to keep the fact that this is corresponds to one particular edge. This one corresponds to this edge. This corresponds to this edge. This is so on and so forth. Okay, so you're transferring the edge labels to new vertices, right? So why did we win here? We won because we created way more vertices, right? So the number of vertices is much higher here. Every edge in your graph gave 2 new vertices. So we might have increased the number of edges a lot, but that's okay because we are only going to deal with log of the number of vertices. So that's a better bargain to be made. All right. Any other questions about this transformation? Okay. So to summarize, what did we learn from this? So we can assume the input G is a 4 regular graph. We have a target vertex S, sorry, a source vertex S, a target vertex T, and we would like to know are S comma T connected. Okay. And now let's say I denote lambda star of G is the largest spectral gap among, actually, let me not use, actually, so how much space does the brute force algorithm take here? It's going to take log n, right? Plus log of the degree, which is small, which is just log 4, which is just 2 times okay. So in some sense, we at least got rid of the degree problem, but we have to still deal with this 1 over lambda, right? That's coming from the diameter, and we need to control the diameter. We're controlling the diameter by the second largest eigenvalue. And so we need to control that. Okay. Okay. So, with this sort of big idea in mind, the big idea now is we have a graph which has small degree, but potentially very bad second largest eigenvalue. So let's assume the graph is connected for now, because you're only dealing with connected pieces that will kind of show up fit very naturally as we go along. Let's ask ourselves a clean sort of conceptual question. Okay, we'll worry about, okay, space complexity. Can I do this in small space? How do I implement it? What kind of algorithm can do it? But first, are there operations on graphs that can improve, meaning decrease the second largest eigenvalue? Okay, so are there operations which can decrease the second largest eigenvalue of the normalized adjacency matrix? So I give you a graph which has which is d regular. It might be 4 regular, whatever regularity it has, that's okay. Can I improve the second largest eigenvalue? Are there some nice operations to do this? Okay, so we can put aside undirected ST connectivity for now and just think of this sort of seemingly abstract, but as we'll very soon see, very helpful question. Okay, what do you think? Are there any operations which can improve the second largest eigenvalue? Improve meaning you want to decrease the second largest eigenvalue. Okay, and so Alan is suggesting here, in fact, there is one such natural operation, which is squaring a graph. Okay, so let me talk about that. So suggestion, squaring a graph, right? So before doing this, I'm going to mention that we will work with multigraphs. Okay, so multigraph just means that I might have multiple edges between the same 2 vertices. Okay, so here I have 2 edges between 1 and 2, right? So what would the adjacency matrix look like here? So it's 0, 2, 1, 2, 0, 1, 1, 1. Okay. And everything we've discussed goes through without any change. So all definitions, comma, spectral graph theory theorems work as is for multigraphs. Okay. So like, basically degree is the same. Normalized adjacency matrix makes sense. Lambda of G all carry over. Okay, there's no real change. Okay. So what is squaring a graph? So we're going to add a lot of new edges. If u comma v comma v comma w are edges, then add an edge between u comma w. Okay, so you're basically connecting paths of length 2 by short circuiting them. And you delete the old edges, they don't appear. Because we have self loops, they kind of appear, but that's not important, right? So for example, so let's say this is my graph G. Then G squared is going to be this graph. Only the blue edges, right? So I have path of length 2 here, so I connect this. I have path of length 2 here, so I connect this. Okay, and again here, here, and okay, so I went from the pentagon to kind of this star. Okay, so this is the new graph G squared, right? And let's see. And this is not just it, because you're connecting all paths of length 2, right? So you go here, and then the other one is you can also go back, right? So you would also get self loops here. Okay, meaning I go like this and then come back. So that gives me one loop. I go like this and then come back. That gives me the second loop. Okay, this go like this, come back, second loop, and so on. So take 2 hops, and wherever you land, now add a new single hop edge. Okay. All right. You can simplify this by saying, okay, I'm only going to consider, only single instances, a non-multigraph version of this, but it's much nicer to just take the multigraph. All right. So if I do this operation, what happens to the corresponding matrices, right? So you have the adjacency matrix. of G, which is AG. Now, what's the adjacency matrix of G squared? A squared, exactly. In fact, it's much nicer to just take that to be the definition of the adjacency of the squaring a graph. You're essentially squaring the matrix representation. Okay, you're taking paths of length 2 and connecting them. Okay, so I'm not going to kind of prove this, but it's something that you can check offline. So AG squared is exactly AG whole square, right? And not only that, how about the degree? Now, suppose G was D regular. So G is D regular. What is going to be the degree of G squared? Think of this example. What happened? So the degree was 2. It became 4 because you have one option. I take any one of these D edges, and then I can take any of the D edges from this wherever I land up, right? So it's exactly D squared. Right? So the squaring operation is literally squaring everything in terms of the matrix representations. So the normalized adjacency matrix is also going to be just this square. Okay. Okay. So now, what does this mean? How about the eigenvalues? Right? So the normalized adjacency matrix became squared. So what about the eigenvalues of the new matrix Mg squared? Any suggestions, guesses, what happens to that? Square again, right? So there is this theorem, again, linear algebra. M is a symmetric matrix. With eigenvalues lambda 1, lambda 2, lambda n. Then M squared has same eigenvectors as M. Okay, so the eigenvalues also square. Okay. And one way to say this is, if M times X equals lambda times X, then M times Mx equals lambda times Mx equals lambda squared times X. Okay. But again, this is basics of linear algebra, so we are not going to prove this, but take it for granted. Okay. So what does this mean? So it means that the second largest eigenvalue of G squared is just lambda of G whole square. Okay. And since lambda is something less than or equal to 1, you are actually improving the second largest eigenvalue. You're decreasing the second largest eigenvalue. If lambda of g was 0.9, the new one is 0.9 squared, which is 0.81. Okay. So in particular, this implies that G is a ND lambda graph, then G squared is a ND squared lambda squared graph. Okay, so the number of vertices did not change. The degree squared. So kind of we hurt ourselves in the degree, but the second largest eigenvalue improved. It went from lambda to lambda squared. Now note, as lambda is less than or equal to 1, lambda squared is less. Okay. All right. So this is some operation which improves the second largest eigenvalue, but it hurt the degree. Okay, so we paid something in the degree. So let's see if this is a trade-off that is worth making. Is it giving us a win? Okay. So in what sense would it be a win? So here, the brute force algorithm has space, which is, there is log n, which is fine. So let's not worry about that because that's not the dominant term. Plus, you have log d times log n 1 over lambda. Again, ignore the constant factors. So you have log n 1 over lambda, right? So this was what we were getting from using spectral graph theory theorem number 3, because diameter is at most that much. Now, if I use this guy, what happens? I still have log n. That is fine. Let's not worry about that. Now, the degree became square. So we improved there. But, sorry, the degree became square, so it's worse. But we improved here. Okay. Is this a winning trade-off? So did we gain anything by doing this? What do you think? Well, actually, so let's work this out, right? So what is this guy? So log of d square is just 2 times log d, right? Exactly, it's the same because on the other hand, this is log n 1 over lambda and it is exactly equal. There's no loss here. And for any alpha, this is 2. Log n of alpha squared is exactly half of log n base alpha. Okay, so that means that these two things cancel out and we gain nothing. Okay, so this is something, so much ado about nothing. We had this nice squaring operation. The linear algebra worked out very well. All the eigenvalues, eigenvectors worked out beautifully, but it gave us no gain in the final trade-off, right? So as you were asking, is there a trade-off between degree and lambda? Yes, there is. I can kind of increase the degree and decrease the lambda, but they're kind of happening at a rate which is not giving us a win, right? This is squared. That kind of got also squared, so you didn't win anything. Okay, so we need to see if we can beat this specific trade-off of squaring, right? So find a powering operation. This happened for the square. You might say, okay, what happens if I take the third power, fourth power, fifth power? None of those work. All of them kind of end up with the same exact bottleneck. You improve the degree, you increase the degree at the same rate that you're improving your spectral gap. So you end up with no gains in the end. Okay. So we need to find a powering operation that improves the second largest eigenvalue while not increasing the degree too much. Okay. And this is exactly what Reingold did. And in some sense, he used an existing powering operation, and studying that powering operation is worthwhile just for its own sake. But let me write that main template down. Okay. So we're going to start with a special graph, which we'll call it H. It's a fixed graph with some number of vertices, maybe 16 vertices, 10 edges, some fixed graph, special graph, right? So we have G, S, and T. Remember, this is 4 regular. We are going to assume that. And it also has self loops. Okay. So what we're going to do is first do the square. Do the squaring operation, which improves the second largest eigenvalue, but hurts the degree. And then we're going to bring the degree down. Right? So we kind of saw a trick to reduce the degree already, right? So this trick reduced the degree. But the point is that it doesn't help, or it can really hurt with the second largest eigenvalue. So we need a version which can reduce the degree again, but not hurt the second largest eigenvalue. So this is where the special product called zigzag product comes in. Okay, so every time we are going to replace the graph that we currently have with a new graph, which is the square of the current graph. So the same thing that we started out with, squaring, which improved the second largest eigenvalue, but hurt the degree, and then do something else to reduce the degree, but not hurt the second largest eigenvalue. Okay, so this is like decreases okay. So in some sense, zigzag product is kind of a more advanced version of, wait, where did that go? This replacing with cycle operation we did. Okay, so it's kind of an advanced version of this where you reduce the degree, but you do not hurt the second eigenvalue too much, right? So we have to do both. It's some kind of alchemy, it almost sounds like alchemy because I did something to improve one parameter, but hurt the other. And now I'm going to do the other thing to kind of undo that damage. And you need to make sure that in the end, you win out. Okay? And in the next lecture, when we come back, we will talk about this really, really beautiful idea called zigzag product, which has found tons of applications since. And this is actually due to Reingold, Vadan, and Wigderson from 2001. Okay, so this product had been studied earlier, and we're just going to kind of use it for this specific application. All right. So next week, hopefully in person on Monday, we'll talk about zigzag product. As I said, it's kind of a beautiful idea on its own. There's tons of applications in math and everywhere else. Okay. Besides the undirected ST connectivity problem. In fact, it was studied and introduced well before its application to USDCon, but it's kind of very useful. Okay. All right. I'll see you all on Monday. Bye. Bye, everyone.